Good morning, good afternoon, and good evening, everyone. So today we're going to be going over part three of my midterm one review. So yeah, let's just hop right into it. So for my part three here, I'm basically going to be going over vector functions, a little bit of derivatives and integrals, no, not a little bit, a lot. Arc lengths and curvatures. So yeah, let's just hop right into it. Okay, so the first thing that we're being asked to do, so okay, I'm just taking a screenshot there. So here, yeah, this is long, but basically they want us to set up an integral that gives the arc length of the curve of intersection of the cylinder x squared plus y squared equals 4 and the plane z equals 3x. And we're given a hint here. First, we need to find parametric equations for the curve of intersection. And again, don't try to evaluate the integral. So just set it up with the correct bounds and integrand and write your integral below. Okay, so basically we want to find the length of the curve of intersection between a cylinder and a plane. So how could we visualize that? Well, we can say, okay, I have a cylinder, I have a cylinder, I have a plane, and their intersection is this thing, right? Okay, so I have to find parametric equations for this red thing. So this is the intersection curve. So we want to find parametric equations for that because we want to describe that curve, right? So how do we do that? Well, okay. Well, we want to intersect, basically, right? So the way we're going to intersect is, well, we need the two equations of the two surfaces, right? So we have a cylinder here, and we also have the surface equation of a plane, where I wrote equals z equals 3x. Okay, now what can we do here? So the idea is we want our x, our y, our z. We want them to be of some function that involves a parameter, and we'll call it t, right? That's what we want. So how do we do that? Well, okay, we can say this thing could be equal to 4 cosine squared of t plus 4 sine squared of t, which is equal to 4. How do I know this? Well, cosine squared plus sine squared is 1. It's a basic trigonometry identity. And so from here, well, we can say that, let me move this. We can say that x squared is equal to 4 cosine squared of t, and my y squared is equal to 4 sine squared of t, right? And then from here, we can just get our x value. So that's 2 cosine t. My y value is 2 sine t. So now we have x and y in terms of t. Now we just need to find z. So here z is 3x. So we can say 3 times our x value in terms of t, and we will actually get a nice number here, 6 cosine of t. And so our parametric equations are as follows: x2 cosine of t, y2 sine of t, and z 6 cosine of t. And these parametric equations describe this curve, the behavior of this curve. Okay, and now we want to find the length of this curve, right? And so to do that, well, we need to set up a vector function of this curve. Well, we can do that. We can say, okay, well, this is just the same as, let's name it r of t, 2 cosine t, 2 sine t, 6 cosine t. So that's our vector function for this curve. And now we actually want to get its derivative, right? So here we want to set up integral for arc length, or for the length of this curve. And so the way to do that, well, let's say some arc length L, the integral from some bounds, A to B maybe, and this is just the magnitude of the derivative of my vector function. So it's the magnitude of my tangent vector, dt. And so how do I find my A and B? I also need to find that actually. Well, judging from this, we can see that t is in between 0 to 2 pi. Why is that? Well, this is a circle, right? There's a circle. And in a circle, well, t can only be 0 to 2 pi, or at least the angle. Because if it goes beyond, well, it's exceeding 1 revolution, and we don't want that, right? So here we say my A is actually just 0, and my B is actually just 2 pi, right? Now I can set up an integral. So to set this up, well, okay, we have that. And then now we can plug in what we know. So A is 0, B is not pi, B is 2 pi. And we want the magnitude of the derivative. Okay, actually we need to get that one first. Let's get that one real quick. So the magnitude, or let's do the derivative first. So my tangent vector is 2 negative sine t, so minus 2 sine of t. Well, 2 sine t, so that's the derivative is 2 cosine t. And then we have another one, 6 cosine t, so that's negative 6 sine t. And this will give us, we can now get its magnitude. So this is square root of all of this, right? Okay. Now we can actually simplify this whole thing. We can say this is 4 sine squared of t plus 4 cosine squared of t plus 36 sine squared of t. Nice. Now I can even add together. So we have 4t sine squared of t plus 4 cosine squared of t. Okay, have I simplified it? Well, not really. In fact, there's another way I could have written this. Instead of going this direction, I could have factored out the 4 and turned this into a 1, right? So I could have said, oh, okay, maybe I don't want to write it this way, but this is totally fine. But I could have said something like, oh, I could factor out the 4 of my two terms, and look at that. I have a trig identity, right? So here I have 4, yeah, here I have 4 plus 36 sine squared of t, right? That's what I have. Um, yeah, pretty much. So now my length is just something that goes from 0 to 2 pi with this integral. Right? Dt. And I'm done. Set it up. Easy peasy. Let's see if I got it here. Yeah, so here I did it a little bit differently. So here I got 4 sine squared, 36 sine squared, 4 cosine squared. Yeah, I did it a little bit differently there. This one I tried doing it this way. Just so that's nice to look at. Okay. So that's that. Okay, next question. So here we're given, I'm just looking at my old stuff here. Here we're given a velocity of an object. So we're given this. So the velocity vector here, right? So this gives me my direction at time t seconds. Okay, and its initial position is this. So our task here is to find the vector function, the position vector, r of t at time t. So here really, the first thing we think of is integrate, right? So here we're gonna immediately integrate. So we're gonna integrate r prime of t, and then we're also going to integrate its component functions. dt, 5 dt, t to the power of t squared dt. Okay, cool. And let's integrate them one by one. So we can take out that 2, and we have sine of t dt, and we can see, oh, this is just minus cosine. Minus 2 cosine of t plus some constant. So let's say c1. And then, okay, we have a 5 dt. Oh, well, this is just 5t plus c2. Then we have this other one. T equals, or not t equals, t times e to the t to the 2. Here we can use a u sub, right? So we can say t squared. T, where was I? I could say my u is t squared. And then if I if I get its derivative, so I get du, this is just 2t dt. So my dt is just, well, 1 over 2t du. And so if I combine all of those stuff, well, I get t e to the u, and then my dt is just 1 over 2t du. And here I get to cancel out my t. So I get 1/2 of e to the u du. And I can I can do this plus some constant c3. But again, my u is t squared, so I get e t squared over 2 plus c3. So this is the problem with integration. It's quite long. But we're Gucci. Okay. So now we can write our vectors here. So we said for my x component, it's this guy right here. But the only problem with these components, component functions is that there's a constant that we don't know. Well, we're going to find a way to actually get the number of these constants. And so the way to find these constants is we're going to use that information we got earlier. No, now we got the given info, which was r of 0 is that. So we have here a given position vector that tells us if our parameter t is 0, this is our position vector. This is where we're at. And so, okay, well, how do we make use of this, right? Well, here we have our position vector. So we just plug in 0, right? So we're saying our x component at 0 plus c1 is equal to 0. And notice here, we can solve this because it's one equation and we have one unknown. And so if we solve this, well, that's just c1 equals 2. Because cosine of 0 is 1, negative 2 plus c1 is 0. So that means c1 here is 2. And we do the same for the others. So 5t plus c2 is equal to, in this case, 0. 0. And so we say, oh, c2. Oh, crap. I forgot to plug in the 0 here. 5 times 0. c2 here is definitely 0, right? And if we plug in our last one, et squared over 2 plus c3, and we say that's, oh, so now this is 1. Well, we say c3 is just, this is 1/2. So c3 is just 1/2. And now we have our vector function here. So my r of t is negative 2 cosine of t. And instead of adding our constant, we add the value we got from it, which was 2. Next thing is we have 5t plus c2. c2 is 0, so we just say 5t for our y component. And lastly, for our z component, well, et squared over 2 plus c3. So c3 is just 1/2. And there we have it. Done. That's our position vector. Okay. Next thing we want to find is the, okay, next item. So this is a curvature question. So let's quickly go through it. I might actually go through some other stuff here maybe, if time allows. So to find the curvature of the curve given by r of t at t equals 0, well, we already have our r of t, which was this one. So to find a curvature k, what do we need? We need the cross product of its first derivative and its second derivative all over the magnitude of its first derivative cubed. So this is just something that was given to a formula. This was just a formula given. So we know what r prime of t is, right? That's what we have that right there. Now we want to get r prime of 0, right? So here we want to find the curvature at k of 0, right? So here actually I'm gonna switch all of the t's, make them 0, because that's what we're being asked to find, right? Okay, now let's find r prime of 0. R prime of 0, if we go back here, 2 sine of 0, that's 0, 5, 0, 0, 5, 0. Sine of 0 is 0. 0, 5, 0. Done. R double prime, that is, oh, I haven't gotten a function of the second derivative yet. So let me just do that real quick. So my R double prime of t is, well, you take the derivative of each component. So we have 2 sine t. The derivative of that is 2 cosine t. Next, we have the derivative of 5, that's 0. And the derivative of det squared. So we want to find the derivative of this thing. So I know this is quite long. But the derivative of this thing, well, we do a product rule. That's what I would do. Okay, and this is going to be, okay, this is going to be E. I don't need to do this. I add T. This one's going to be what? The same thing times chain rule. And this is going to be 2t. And there we have it. So we have et squared plus 2t squared, because we multiply that too. Et squared, I can factor out. Et squared is just 1 plus 2t squared. That's it. So that is et squared. And then what I say? 1 plus 2t squared. Done. That's the derivative. How do I know if it's right? Integrated. I'm kidding. I don't want to do that. Okay. Cool. I mean, I could for fun, but I don't want to. Okay. So now that we have that, let's plug in the zeros. So this is cosine of 0 is 1. So I got 2 times 1 here. This is constant number 0. This is a 1. 1 plus 0. So that's just 1. Nice. Now we got their cross product. So that's I, J, K. Okay, here I get 0, 5, 0, 2, 0, 1. I continue. I cancel out my ones. I get 5 minus 0 for my I. Drop my J. 0 minus 0 for my J. Then I add 0. What's this? 0 minus 10 for my K. And so I get 5, 0, negative 10. Okay. Now I get that length. So I get the length of this thing. It's just the distance formula. This is just 25 plus 100. So 125. This is what is that? Any chance? Oh, okay, so it's actually just 5 squared 5. Okay. And then we can get r prime of 0. Let's get that as well. And we cube it to 3. Let's quickly get that. My r prime of 0 was 0, 5, 0. So I get 0 squared, 5 squared, 0 squared. Cube that to 3. I get 5 squared 3. I got 5 to the third. And well, yeah, I'm okay with that. And so my curvature at equals 0, my curvature is 5 square root 5 over 5 cubed. I can cancel some stuff out. So this is just square root 5 over 5 squared. Let me see what I got previously. Yeah, it's the same. Square root of 125 over 125. Yeah, so that's just again 5 square root 5. This is 5 cubed. I get to cancel. This is square root of 5. This is 5 squared, which is exactly the one we got. Okay, yeah, let's do some more problems, yeah? Might do more problems here. That was it for like the whole midterm review. I might just go ahead and do more problems, because why not? I might go to the homework maybe, or yeah, let's just go for it. I mean, we're here, so let's just do it. Okay. Uh, I'm thinking of what to do. Okay, maybe I'll do something from one of my exercises, maybe. Let's do something from each week. Do I just do that? Pick something hard. Uh, we can do that distance formula. We can do that. Or maybe, I don't know, something from 12.2. Really hard to pick problems here. So, I'm just gonna go for one and see if I don't know, if I like it, maybe. Yeah, honestly, I'm just gonna go for one of them. Oh, maybe more projection stuff, maybe? Or, hmm. Yeah, I'm gonna just do maybe like a hard website, a hard exercise. I'm just gonna do one at random. Okay, so let's just go for it. What's the hard one? Describe points. Oh, what is this? Describe the set of points? What does that mean? Okay. Um, okay, let me do one from uh something a while back. Oh, is this given? I'm not sure if it's given. I totally forgot. Uh, okay, maybe I'll do some homework problems. Okay, let me just go for it. Uh, let's see. Because I hope I don't wanna ruin my preparation, and I might just go for a completely different problem, which is uh, okay. Okay, maybe let's look at vectors. Let's try that. Okay, let's go for it. So for vectors, well, I think the hardest one would be something related to the pulling one. So I'm gonna do one of those. Okay, let me just do one of those. I think it was the last one. The last problem was really hard. Yeah, it was really hard. Um, shit, that's funny. Ah, found that weird. Oh, they made it. Oh, that's funny. Okay, so here's one problem that I think is hard. So here, I'm just copy paste it. Doesn't matter. I think one problem here is this. This one looks hard. We're being asked to find the magnitude of the resultant force and the angle it makes with the positive x-axis. How do I go about that? Well, what is the resultant force, right? The resultant force is this thing, right? Because if I add the two vectors, I get the resultant force. The sum of the two vectors is the resultant force. These are two force vectors, right? Because it's in newtons. Um, what else can I say about it? They're asking me to find the magnitude, so they're asking me to find the length of this resultant force and the angle it makes with the positive x-axis. So it's asking for this angle, if I'm not mistaken. So how do we do that? Well, my approach here would be, okay, I can take a look at this vector, right? This is a vector. And I want to try to say that's v1, that's v2. And I'm saying this is v3. So the idea here is v1 plus v2 is v3. So if I'm going to say v1 has some change in x and some change in y, right? And this has 200. So I can just say, okay, maybe that's just 1 over 200. That's the easiest way. And then for my v2, I can say, okay, that's just 500, right? Change of 500 here, 0 here. Okay, now what's my v3? Well, v3 is just addition of these two. So if I add these two things, well, I get a new vector. I get 501, 200, which is my v3. So it's this one, right? That's my new vector. Oh, how do I find its magnitude? So to find the magnitude, well, I want to use a distance formula here. 501 squared plus 200 squared. This will give me, well, let's see. 501 squared. Oh my goodness. Okay. It gives me that. It gives me a big number, basically. You know, let's just copy it. 251001. I added to 200 squared, 40,000. Okay. I added to 40,000. I got 291,001. And if I take the square root of that, is it possible maybe? Okay, it's not possible. So that's my length. And now, actually, I could just 291,001. I can see if I got the right answer anyways. So that's approximately 539.4. And what's the length here? I'm gonna say meters. I don't know. Units. Ooh, so I actually got it wrong. Yeah, I got it wrong. So what in the world am I doing? Okay, let's see. Uh, where was this? Where was this item? Yeah, so I find the sum. Hmm. Ooh, I did something completely different here. So here I did something really different. Yeah, I totally forgot what I did here. So I did a tangent. Why did I do a tangent here? Well, okay. A plus B gives me that. Oh, yeah. So this is a plus b. Okay, I did a plus b. And then I'm trying to find this angle here. Or I have this angle here. So I get a tangent. And I get a tangent of theta is square root of 3 over 4. Which is interesting. Cool. Okay. Now what did I do? I got an angle out of it. Now I subtract, I get the angle. Okay, but how did I get the magnitude? Oh, I added. And then I get there. Huh. Find both vectors. Yeah. Negative 500, 0. How did I know this was 100 and 100 square root of 3? Oh, because I did a cosine. And I know this is 200. So the length of this thing was 200, right? Because force is a length. Let me see. Definition of vectors. Hmm. Force, displacement, acceleration. So actually what was given is the length of that vector. It wasn't the actual vector itself. Yeah. Yeah, I was definitely wrong there. Okay, well now I know how to do it. See, that's math. You never get it the first try. I'm kidding. Sometimes you do get it the first try, but here in my case, I don't. Well, at least it's a learning experience. So let's just enjoy the thing. Okay, so first we have to find the two vectors. Okay, let's say this is v1 and v2. I'm not gonna use AB. Okay. So there has to be some resulting vector here because we want a resultant force. This is v1 plus v2. Let's just say that's v3. Okay. And we're trying to find the magnitude of this thing, so how long it is. And we're also trying to find the angle it makes. So we're trying to find this thing. Okay, so first thing we can do is find its magnitude, right? First, we need to find two vectors for these guys. So we can say v2 easily. V2 has negative 500 because it goes to the left, and then 0 for my change in y here. V1, on the other hand, is a bit more complicated because I have a 60 degrees here, right? I have a 60 degrees, and I know 200 here, but I don't know these stuff. But this is my change in x. This is my change in y. So how do I find each of them? Well, I can say, okay, find my change in x. Well, I can say, I can do a cosine, right? So I can do some trig stuff here. So I can say, okay, that's also something I have to know. I have a cosine of 60 here, which is just my adjacent, so my delta x over 200. Oh, look at that. My delta x, now I found it, is 200 cosine of 60 degrees. And similarly for my y, well, I can say the same thing. Now this is sine of 60 degrees, which is my opposite side. So delta y over 200. And so my delta y is 200 sine 60. So the key here is labeling unknowns. And so my vector here has these guys. Nice. Okay, now I got those. Now what? Uh, I need to find B3. Goodness gracious. Uh, yeah. Also, another thing I need to do actually is find cosine of 60. Yeah, that's another thing I need to do. Uh, Cosine of 60 is 1/2, luckily. So that's 100. And then sine of 60, I hope is a nice number. It's not. So I have to look at the trig table to do this. Um, yeah, let's quickly do that. I'm gonna have a trig table for an example. So sine of 60 is square root of 3 over 2. Okay, so I get 100 square root 3. Okay, what else? Yeah, now I can change this to be what I want it to be, which is 100 for my x and 100 square root 3 for my y. Good. Now I have concrete values. Now what's next? I need to find my resultant vector, or my sum, which is this guy over here, my green vector here, and I want to find its magnitude. So I'm going to add these two vectors to get my v3, because that's what I need. So v3 is my is the sum of my two vectors here plus my other one. And this should give me a nice value actually. This is negative 400, comma, 100 square root 3. And this makes sense, right? Because I'm moving to the left, negative 400, and I'm moving up 100 square root of 3. And so now I have my vector. Now I want to find its magnitude because that's what I was asking previously. So let me just quickly do that. So I just basically get all of its components, square them, and I should get something. Okay, here it's a bit unusual. 160k. We multiply 100 squared is 10,000 times 3, so that's 30,000. That's not 6, that's a 0. Yeah, because 100 times itself, I got 10,000, right? So I'm referring to this thing. I multiplied to 3, so I get 30,000. And I just add them, so I got 190. 90k. Then I square root that. Can I do it? Yeah. So when I square root that thing, I got 435.9 magnitude, so I get 10. And so that's that. Did I get that? Okay, finally got it. Now I need to find the angle it formed. So from here to here, right? Now, my idea here is to probably use the dot product to do it. But I don't think they taught us that one yet. So I know there was another way. But you know what? I'm gonna try it. I'm gonna see if it works. So I'm gonna look at this vector here. I'm gonna look at that vector. I'm gonna say that's V4. I'm gonna get the dot product of that to get this angle. So what is this? Oh shoot. I actually don't know what that is. Oh, that's funny. Okay. Uh, or maybe I could get the dot product of these two because these two are the ones I know. And then I just add 60 and then that's it. Another thing I'm thinking of, yeah. Or I can get the dot product of this one, get that angle, and then subtract 180 to it. Either way, let me see if I can get the answer when I do. I really want to try it. Maybe get the dot product of my V1 and V3 and then just add 60. I want to see what happens. Okay, let's do it. So to find my angle, I'm going to try something nice here. I'm going to say my dot product of V1 and V3 is their magnitudes. Uh, Cosine theta, right? And so what's the dot product of those two? 100 and 100 square root of 3. Oof. Okay, that is a nasty computation. Maybe that's why they, yeah, maybe there was an easier way to do this, which I totally forgot. Uh, should be somewhere here, maybe. Yeah, once I get that, I find their sum, magnitude, done. Oh, I use a tangent. That's smart. Yeah, here I use the tangent to find this angle. Um, yeah, and I subtract. Wait, let me actually try to get this. Yeah, let me try. I'm not gonna try the other one though. This one's looks complicated. Let me try the other one. I'm gonna try this vector here, V2 and V3. I'm gonna try to get that angle first and then subtract it. So yeah, let's see. So what was it? V2 and V3. Yeah, let's do V3 dot product of V3 and V2. Let me see. Then we got, am I doing it right? Yep. Then we get their cosine, let's say alpha. And then yeah, I'm just playing around. Let me see. Let's see if we can get it. Okay, okay. So we have V3 and V2. Let's try to compute that. Well, that's just V3, this vector here, dot product of V2 vector. So this thing here. Whew, still a messy thing, but doesn't matter. Here I get this times this. So that's a positive number now. So that's 200,000. Then I add it to 0. So that's that. And then I get V3 and V2. So my magnitude of V3 should be what? Oh, my magnitude of V3 is this one. So let me not round off for a while. Okay. Let me actually just be exact here. Okay. Then my V2. Well, V2 should be easier, right? Yeah, because I just do this. So it's a square root of 500 squared, which is just, yeah, I mean, I square that thing plus 0 squared. Well, this is just 500, pretty much. And then I have a cosine alpha here. Okay, let's see. Now this is the fun part. We have 200,000. We equate it to this thing, so 500. Man, these are long numbers. Cosine alpha. Now I isolate alpha here, so I can say, okay, uh, I divide 200 divided by this thing is equal to my cosine alpha. I can actually cancel two zeros here. What else can I do? Oh, that's fine. So I could just say my alpha is arc cosine. of 2,000, 5, 190,000. It was just approximately some number that, yeah. So it's arc cosine, and this is in degrees, right? Arc cosine of 2,000, I divide it by uh 5 square root 190, 123. Let's see if we get that. Oh, look at that. Yeah, let me try to write everything. 4, 4, 5. Then we subtract that too. Yeah, so I got this thing. I subtract 180. That thing. So 180 minus this thing. Yeah. Wait, let me see if I got it. Yeah, I got the same thing. So minus this thing is around 156.6 degrees. So yeah, I was just playing around. Yeah, I could have used tangents. But I decided to do dot products instead. Oh yeah, that was fun. That was really fun. Using vectors instead of trig. Yeah. Yeah, here I get the same thing. That's really cool. Anyways, yeah, can we do one more maybe? Maybe one more? Or is that good? Let me see if there's one more that I had a hard time with. Find unit vectors. So that's something I have to look out for. Describing set of points. That seems fine. What else can I do? Maybe I can do 12.3. Yeah, how about something with dot products? Let me see. There might be something difficult here. If U is a unit vector, find their dot products. Assume V and W are also unit vectors. Oh, okay, this one's interesting. Let's do this, and then yeah, here I'm just exploring, I'm just having fun. Okay. Let's try this. Uh, say, yeah, here I'm just exploring at this point. Um, okay, see if we can try to have some fun here. Okay, so so this is, here we assume we only know dot products, but I'm gonna use everything I know. Here we assume U is a unit vector. Their dot product of U and V. Oh, we have to find those two. Oh, that's cool. Well, what do we know? If U is a unit vector, then that means the length of that vector is 1, right? So long that if they're 1, that means the length of V, well, actually, the length of all of them is 1, right? Because this is it looks like an equilateral. Yeah. So I'm gonna assume, right? If it's equilateral, let me see. No, I actually can't assume. Does it have equal sides or only equal angles? Yeah, it should have equal sides and angles. And we can actually say, oh, the angles they form are 60, right? So that's a fun fact. Okay, let's look at the dot product of these two things, U and V. Um, well, what is this? Uh, Is there a way to figure out how this works? Okay. Oh, we can use yeah, because we're given angles, so we might as well use this, right? Yeah, we could use that. And we know the dot product. Actually, I don't know the dot product. All I know is that their lengths are 1. So I'm left with cosine theta. So I'm actually left with cosine 60 in this case, because I know that, because they're equilateral. And cosine 60 is 1/2, right? Yeah. So that's a clever thing to do. So now we know the dot product of these two is 1/2. Now let's talk U and W. Actually, here's the funny thing. If we notice the arrows, right? We're saying that U plus V is W, right? Or U plus W is V. We can see that. Yeah. Uh, what else can we say? Um, I mean, yeah, U plus V is W. What do I do here? Oh, I don't know. Um, that's tricky. Yeah, that's also one more thing that we have to figure out. How do we get the dot product of U and W? Because this is different, right? Uh, yeah, because I already know the answer. It's different. U and W? U? Oh, it has something to do with their angles. Yeah, something to do with that. Actually, you know what? I give up. I don't know. I'm gonna check. So the thing about math is knowing when to give up and then just checking it, right? So let me pull up that example. If I did it. Did I do it? Oh, there you are. Even the screenshot. Oh, there we go. So here we say 120 when I get the U and W here. Why is it 120? That's interesting. Oh, well that. I get a parallel W here. I get an extra 60 because this is a parallelogram. Oh, okay, that was clever. That was really clever. Yeah. So to get that, like the arrows pointing outside, and then you know that's the angle. Because here the arrows are pointing there. So we know there's a problem. So we want to do something like, okay, maybe make a parallel. That's also the same W. Same magnitude, same, well, not same components, but it's parallel. And here there's an extra 60, right? And so the dot product of these two is when cosine, well, their angle is 120, right? So U by W, yeah, again, their lengths are 1, but their cosine is 120. And so that's negative 1/2. So yeah, just some interesting stuff here. But yeah, that makes sense. Yeah, and even here, if we do VW, we need to put the W to this side now. And we should get the same angle, 60. Yeah. Okay, that was fun. Okay, let me actually do let me do an interesting one. Acute angles, scalar. Find the angle between a diagonal of a cube and one of its edges. It's one of these. Okay, yeah. Let's do something from my current stuff because I still haven't done much of that in a while. Okay, let me just go for it. And then this is my last one, then we'll just call it a day. Yeah. Okay, let's look at maybe something from, I don't know. This one I'm just picking at random. I'm just seeing if it works. Okay, let me pick a, let's do something about vector equations. Yeah, let's do that. Vector equations and space curves. Uh, let's do the last one. Okay, never mind, not the last one. Because I already know how to do this. Uh, okay, you know what? How do I, maybe not web assigned problem. Maybe not that. Let's look at some exercises from my professor. Let's do that. Okay, I'll just pick one that, okay, let me just pick one. And then that's it. We'll call it a day. Okay, let's do something from, what is this? What in the world? What am I looking at? Okay, that's funny. Uh, exam archive. Hmm. I mean, he did like page 4? Is this? Is this a thing? Okay. Part 1, lines and planes, surface names. Maybe we can do something with surface. Oh, oh crap. There's not an exam here. Uh, or is this the one that he gave? Oh, this is the one he gave. Oh, shoot. Okay. Maybe spring? Okay, let me see. Okay, let's do. I don't know. I'm just doing one at random. Okay, here's oh, it's like a multi. There's a determine whether each statement is true or false. That's okay. That's so bad. That's actually bad. Find the arc length, the elliptic cylinder, surface. Do we do that? Constants, curvature, zeros in the air, acceleration. No, we didn't do that. Okay, let's do the first one because that one's funny. Okay, uh, let's try this one. I don't know, I'm just doing it for fun. Okay, let's see. Let me go over and do this. Oh, is it visible? Oh, there you are. I'm gonna go a bit down. Okay. Now here I'm just going through random problems. I'm just seeing if I can get them because I'm pretty much done with practicing. Okay, so we have a parallelogram below, and it has corners at A, B, C, and D. Okay, the point E is discussed in the last question on this page. What? Oh, the last question. You are given the following. Did it say something about E? Oh, it did. Okay. We're given the following information. So the location of A, okay, so these have points. So this is 1, 2, 3. And B here has, I can't write it, 2, 3, 5. Vector AD, so A to D, so it's saying all the way to here, is 3, -1, 0. So usually when I'm doing math, I just like to draw stuff, see where it goes. So here I can find point D, actually. I'm being asked to find the XY coordinates of point C. Ooh. Okay. Okay, okay, okay. So we can actually just use this vector AD, this BC, right? We can just use that. Do I know where to get the answer key just in case? I think we could just use that. There we go. There's the solutions. Oh, and we have a video. It's so convenient. That's really nice. Yeah, that's really nice. Okay, I'm just gonna go through. Is this the solution? No, it's not. Okay, I'm gonna hit the solution, see if I don't get it. Okay, so here's my attempt. I'm gonna use the same vector. Why? Because I know they're parallel, right? I know the vectors here are parallel. So what I'm saying here is that AD is actually parallel to BC. And so I could probably use the same vector, right? So if I just add some stuff here, then C should have, well, what's this? 2 plus 3. I get 5. Uh, 3 plus -1, I get 2. 5 plus 0, I get 5. And I'm done. Did I get it? Oh, I got it. Nice. Yeah, that's it. That's funny. Okay, got that. Okay, now we're being asked to find the area of the parallelogram. Let me just take a screenshot. And give the equation of the plane containing this parallelogram. So what does that mean? Okay, so here we want to find the area of the parallelogram. What do we know? Well, if we get the dot product of two vectors, then we can find the area of the parallelogram. So we can say, okay, we have AD, right? Now we just need to get AB. So let's just do that. And the way to do that, well, we need to subtract B from A, the components. So here we need basically two vectors. So here we're actually given the vector AD, 3, -1, 0. We just need A to B. So this is 1 plus 1, that gives us 2. So my vector here is 1. Right? So I need this vector as well. That'll give me AB. 1 plus 1 is 2. 2 plus 1 is 3. And 3 plus 2 is 5. So there we go. I have my two vectors. Now I get their dot product, right? Doesn't matter which one. I don't think so. If I get the dot product of any, doesn't matter. The order, I mean. So we get 3 times 1 plus -1 times 1 plus 0 times 2. Well, I get 3 minus 1, I get 2. So the area of the parallelogram is 2. That's it. As simple as that. And oh, my bad. I actually do a cross product. What? Okay, my bad. They do a cross product here. Oh, so it's the magnitude and their cross product. My bad. So I have to. Okay, I got these two. Wow. Okay, not intuitive. I get their cross product and the magnitude of that. So that's what I have to do. I was like, wait, I got a different answer. That's that's annoying. Okay, let me just do a cross product here. Okay, this will give me -1 times 2, it's -2, minus this is a 0. I get I, minus I take out my j's, I get 6 minus 0, it's my j. I add, I take out my k's, I get 3 3 minus -1, so that's 3 plus 1. That's my k. And then here I got -2, -6, and 4. Then I get the magnitude of that thing. So this will give me square root. Done. I got 4, 36, 16. 56, square root of 56. And that's it. That's my area of parallelogram. Now I need to find the equation of the plane containing this parallelogram. So how in the world do I do that? Well, let's think about it. Equation of the plane. It contains this parallelogram. Well, I have two vectors. Let's say this was the plane. I have two vectors here, right? I could make use of that. I just need to find one of the points. What do we need for, oh, actually, yeah. What do we need for a plane? We need a point and a normal vector. And we actually just got the normal vector here. And so the point we could use as any, to be honest. We could just use a 1, 2, 3. Let's just use that. So an equation of the plane could be, so the plane equation is, well, it's just A. So A is ABC, normal vector. So it's just this one, -2, x minus 1, -6, y minus 2, plus 4z minus 3. Done. That's my plane. Those are my two stuffs, right? Yeah, I got the exact same thing here. Oh, so we did. Okay. Yeah, it's fine. We got the same thing. Cool, cool, cool. Yeah, we got the same thing. It was reversed. These things were his positives. This one was his negative, but that's the same thing. I could just multiply everything by -1 and get what he got. It's the same thing. Okay, the next thing we want to do is find the angle BAD. So which is the angle at vertex A, and I have to give my answer in degrees. So again, another cool looking problem here. What I like about this course is it's very visual. I like the visuals. Yeah. So here I want to find BAD. So I want to find this angle. I want to find that thing. Well, voila, we can get that. Now we get the dot product of those two things. Now we need the dot product of those two things. So we get AD dot AB, right? And then this is just equal to their magnitudes. And then their cosine of theta. And then here we just find theta in degrees. So that's pretty much it. If we get our dot product, can you do that? Can't do it mentally. Crap. Okay. Let me just do a complete solution here. 3, -1, 0. Is that right? Cool. Yeah, after this, it's how many more? Oh, last one, then we're good. Might do one of them though. But it's super chill. Okay, then we do 1, 1, 2. Okay, and then here we get 3 times 1 plus negative 1 times 1 plus 0 times 2. And I think we got this already. 3 minus 1 is 2. That's your dot product. Now I get their magnitudes. So AD, 3, negative 1, 0. So 3, negative 1, 0. And I get 9 square root of 10. Okay, now I do AB. So here I do the same thing basically. 1, 1, 2. So 1 squared plus 1 squared plus 2 squared. Here I get 4, 6. I could divide, no, I can't divide. Yeah, and then now I fill in the blanks. So I get this, square root of 10, square root of 6, cosine theta. I could say square root of 60, cosine theta. And I could say theta is arc cosine of 2 over square root of 60, which is approximately some number in degrees. So it's 75 degrees, which seems right. I think so. Yeah, 75 degrees. Yeah. Nice. And lastly, let's do, I want to do the last one. Okay, let's do D. Let's do point E here. Yeah, let's just do that. And then I might do more. I don't know. Depends on my mood. But we'll see. Let's see what we can do. Okay, let's try this out. Okay, for point E, this is, okay, it's on the line segment from A to B, right? The line segment A to B, point E is there, which we can evidently see, right? We can see it there. It's literally there. Now, the line from E to D here, is perpendicular to the line segment AB. Oh, so I need to find the vector D to E. So if I need to find D to E. It's not even like computational, it's just visual. Here we say D to D is perpendicular. Okay, cool. Uh, how do we find D to E? So I'm looking for something different here. I'm looking for a vector that goes here, the other way. Oh, wait a minute. If this is perpendicular to AB, if I want to reverse the sign, I just multiply by a negative to the vector itself. So I can get ED, multiply it by a negative for it to be DE. I could do that. Um, but then let me think. How do I find that? So the thing is, I don't know what E to D is. I don't know that vector. I only know it's perpendicular. Hmm, maybe I can find another vector that's perpendicular. Oh, I just saw something. This might seem dumb, but I'm not super sure. What if I got this vector, right? I get another one. That's perpendicular. How do I do that? Well, I just do a negative sign. Then I do a cross product of that, and then I get E to D. What if I do that? That's fun. Um, what else does it say? Yeah, that's all it says. E is on A to B. I don't know what the point is. Line from E to D is perpendicular to the line segment from A to B. Now I need to find vector D cross product. I'm thinking cross product vectors dot product. Uh, one of those. I don't know. That is tricky. Maybe wait, one last thing. Yeah, what if I need a vector that's perpendicular? Hmm. Hmm. But I don't know their I mean, what do I know, right? Like area E. E to D. So something about perpendicular, but I don't know what it is. Yeah, honestly, I was thinking of making another vector here. AB. So it means it's also perpendicular to CD. So it means it should also be perpendicular to this thing, right? DC, which is the same vector. Oh, um, I mean, so what if it's the same vector, right? Like, who cares? Okay, I give up. I don't know. What's the solution? Let me see how he did it. Hmm. Oh my God, it's a projection question. AE, wow. How is it a projection question? We project, what does it say? We project AD to AB. Oh, and that will give it, oh, wait, why? I have AD, I have AB. I project AD. What happens if I project it? If I project it, then that means I'm looking for a vector. If I do a comp or I do a scalar projection, then that means I'm looking for a length. So here I project this thing to here and it gives me a shadow. Wait, let me see that real quick. Okay, actually one of the things I'm really bad at is projection. Yeah, if I'm gonna be honest. Where did we learn that? Was it in cross products? Because I was like, yo, and yeah, it's probably somewhere here. I would say. Oh, it's not. Maybe in dot products? Probably in dot products. I think it's in dot products. Yeah, it even has direction angles that we didn't even talk about. Oh, there we go. Projections. Okay, so the thing about projections is if I project A onto B, then I get this vector. Oh no, if I project B onto A, I get this vector because it's like a shadow. Project A to B, I get this thing. So, okay. if I project, let me see. If I project AD to AB, is that what it's saying? Yeah, AD to AB. Here it's saying project B to A. A, how does that look like? Yeah, let me look at some tips here. God, I could never have figured that one out. Yeah, good thing I went over it. But yeah, apparently it's a projection question. But basically, it's this idea here. So for AE, that vector, what? Why is it AE? What happens when I get AE? Oh, now I subtract. What? Wait, what happens if I get AE? Project, and now I get AB vector. I already have that though. Oh no, I got different AE. And now my DE, the one I need. Uh, oh, my D is just AE minus AD. Oh, oh, okay, okay. Yeah, that was, yeah, yeah. Yeah, that makes sense now. Holy moly. There's only two formulas I need to remember for those though. I actually need my fact sheet. Where was it? I need those. Because that one, that's for proofs? Note sheet, yeah. Something for my note sheet, maybe. Yeah. Some projection stuff, because I'll definitely forget this. Oh, okay. Uh, okay, it's there. Okay. Yeah, but basically the idea, okay, if I were to kind of uh okay, I'm just gonna explain this last problem and then I'll call it a day. Actually I'll just draw it here. So basically the idea here, let's just draw this real quick. A crap, I forgot where the others are. B, C, D. So it's here. B, C, D, right? Then my E here goes from here to here, and it's perpendicular. That's my E, right? Is that right? Okay. So the idea here, without even the solving part, is I need to find this vector, D to E. How do I do that? Well, I need to find maybe EA plus, or no, because DE. So what can I say from DE without even knowing anything? DE is basically DA plus AE, right? Now we know, see if I'm right. Yeah. Now we know what AD is. AD is 3, negative 1, and 0. And so my DA, if I want to switch it, then I want to make everything, or I multiply everything by a negative 1. So I get -3, 1, 0. That's it. So I just switched the signs, right? Because in vectors, not even in vectors, if we want to change the sign, then we have to multiply a negative to that vector. We have to scale it by -1. So that's what we're doing here. Now I have dA. That's good. Now I need to find AE. Do I have AE here? No. How do I find AE? How do I find this thing? Well, it's actually, so AE is a projection from AD onto AB. So I project AD to AB. So that's what I do. So I project AD onto AB. And then there's a formula for that, right? Because here, when you project B onto A, you get a new vector. But when you do a scalar projection, you do a comp, you get the length of that vector. So what's the formula for this? Well, if I look back at my notes, because I totally forgot. Something with, was this dot products? I don't think this was, oh crap, I forgot it. I think it was here. Or the formulas. I probably highlighted them somewhere. Oh crap, I didn't highlight them? That's messed up. Uh, oh, there, look, I have it highlighted. No, kind of. Crap, I should have this highlighted. Why didn't I not do that? Let me quickly do that. Yeah, so it's comp AB, A over absolute value of A. So it's comp AB times the unit vector of the one being projected. B projects to A. So yeah, this is just, yeah. Okay, I'm gonna keep my notes there. So this is, again, we just plug it in. So yeah, here we have AD dot product to AB over AB dot product to AB, right? I think that's what it was saying. Oh no, here we get the length. Okay, I'll just follow what my professor did. But I should get the same answer, yeah? And then, what? Yeah, this thing. And then AB here. And then this should give me 2 over 6 of 1, 1, 2. Yeah, which is just 1/3 for 1/3, 1/3, 2, 2/3, I believe. Yeah. And that's my AE. And then now I need to do to get my D, right, is I need to add this thing. I add it to my dA, which is -3, 1, 0. Yeah. And I should get so 1/3 -3, 1/3 plus 1, and then yeah. So I get -8/3, 4 over 3, and 2 over 3. So yeah, that's the vector of the. Wow, that was tricky. That was really tricky. Okay, I hope that helps. At least for me, I hope it helps for me. But I hope you guys enjoyed, learned a lot. I find these topics to be really interesting. I hope they can be applied though. Genuinely, I hope they can be applied in some way, shape, or form. that will help other people, you know. But yeah, I hope you guys enjoyed and learned something. And yeah, I'll see you guys in the next one.